A data structure allows us to store data within our application and retrieve that data as needed. The SPL provides a set of data structures that are well-defined, robust, and tested for our use. Having these SPL-provided data structures can significantly increase our productivity as developers because those data structures provided by the SPL are the common data structures that we would generally need in an application. The fixed array, a linked list, a stack, a queue, and even a tree-based heap are provided in the SPL data structures collection. Arrays are very common. They're easy to use and they're very flexible. The native array that we've been using is not a fixed sized array, which has performance implications. The fixed array data structure is a fixed size. The size must be specified when created. Now, we can always adjust the size if we have to within the application and then pay that performance penalty calling set size. And the fixed array is indexed only. These are not associative arrays. So again, it's a very high speed, random access, indexed array object that we can use within our applications. The functionality provided by the fixed array includes the interfaces for iteration, for using array access, syntax, and to be able to return a count from the contents of the array. And again, the fixed array has performance advantages over the native array. A doubly linked list, such as that provided by the SPL, allows for sequential access to the data. This is not random access such as is available with an array, but we can move forwards or backwards in a list of data. It is not an indexed list, but it allows us to move in either direction through the data. The doubly linked list in the SPL implements interfaces to allow us to iterate over the list of data and even to simulate the functionality of an array by implementing the array access interface, as well as the countable interface, giving us the ability to call the count function, getting the number of elements in the list. A linked list is very memory efficient, and the insertions and deletions from the list are also very, very fast. The stack data structure is a LIFO type data structure, a last in, first out type data structure. When we insert data onto the stack, we push the data onto the stack. When we take data off of the stack, we are popping data from the stack. And the stack is implemented using a doubly linked list. A queue is a FIFO data structure, a first in, first out data structure, like standing in line for a movie. We get in line and we come out of the line in the order in which we entered the line. When we put an object in a queue, that insertion is done at the end of the queue, and we say we are enqueuing an object. When we remove an object from a queue, that object is removed from the front of the queue, and we say that we are dequeuing the object. And again, the queue is implemented using a doubly linked list. A heap provides a very efficient data retrieval structure. The heap is like a tree, where every element in the tree is larger than any of its child elements, which makes searching for a value very efficient. The largest element in the heap is, by definition, the root element, and all elements larger in value to the root element are on one side of the tree and those smaller are on the other side of the tree. The heap in the SPL is implemented as a binary tree, a B tree. However, the heap in the SPL is not a concrete class. This meaning that we cannot create an object of type heap because the heap definition in the SPL contains a function that is declared as abstract, meaning that it must be given meaning by an inheriting class. So the SPL heap must be inherited from. When extending the heap, the child class must implement the functionality of the compare function, again because it's declared as abstract in the SPL heap definition. So our class extending the heap class must provide an implementation for the compare function. Well, the compare function simply defines a way of comparing the value of our objects. Again, because the heap organizes data by value, whether greater than or less than the value of the root, we must define for that heap functionality how it is that our objects can be compared. And then the heap functionality uses that compare function to order our objects within the binary tree structure. To create efficient and thorough error handling in our applications, we can either create our own exception hierarchy that's specific for our application, or we can use the provided exception hierarchy in the SPL. By using the SPL defined exception types, we can build a consistent error handling methodology for our applications. There are two categories of exception classes provided by the standard PHP library. Again, they both inherit from the base class exception. Base class exception, child class logic exception, and the descendants of logic exception are bad function call, exception, domain exception, and so on. And runtime exception is also a child class of the exception class, and it has its own descendant classes, such as overflow exception or range exception. So given this hierarchy of exceptions, we can create a robust error handling system for our application. If we have a need to create our own custom exception, then we can inherit from either exception or based on the type of exception and trying to remain consistent with the conventions of the exceptions within the SPL library, we might inherit from logic exception or runtime exception as well in creating our own custom exception types. So recall from our previous examples using exceptions that there are advantages to using very specific exception types when building our catch hierarchy. Let's go look at some code.